Hello there, Mr. Sutton here, bringing you the Algebra 2 4-8 lesson on analyzing graphs of polynomial functions. For the honors, we'll do this in one shot. For the CP non-honors, this will be a two-parter. So in this lesson, we are going to be graphing polynomials using x-intercepts and some function values, along with the end behavior that we've already been working with. And we will also analyze polynomials graphically using some technology. And then last but not least, we're going to be determining whether a function is even, odd, or neither. For our first example, we're going to be graphing this function that's in intercept form. Now, you might think we've already kind of done this in this chapter. First, we actually had to factor things into intercept form, and then we graphed them. But before, we were just sketching the graphs. We're going to do it with a little bit more precision this time around. Still not 100% accuracy maybe, but closer enough, I guess. So our first step, just like before, is we're going to be finding the x-intercepts, also known as the zeros or roots of our function. So take a moment and figure those out based off of this. Alright, so if we set each of these factors equal to 0, we see that x will equal -3 for this first factor and +2 for this next one. And we actually have a double root of 2. The next thing it would be helpful to know is the end behavior. I mean, we could multiply everything out and figure out the y-intercept, but we don't actually necessarily need to do that. So for finding the end behavior, because this is not already in standard form, there's no lead term to look at. So what we need to do is figure out what the lead term would be if we were to multiply all of this out. So to kind of simulate that process, we're going to multiply the a value, that's this number out in front of the parentheses if it's not an invisible one, and also the x's inside the parentheses together. And that'll tell us what the lead term is going to be. And based off of that, we can figure out the end behavior. So pause the video and see if you can figure out what the end behavior should be. Alright, so we have a positive times an x times, this is actually going to be an x squared. That all comes out to a positive x to the third, which in general is going to be a positive x to an odd power. From before, we know that this is going to be an up line sort of end behavior, where we are starting low and ending high. All right, now what else do we need? Well, we also need to know a little bit more about what's happening between these zeros. We know that to the left and the right of the zeros, this end behavior is going to help us out with kind of piecing together where that polynomial is going, but we don't know much about what's happening in between them. So we're also going to plug in some x values between the x-intercepts, and that'll give us some additional points. Since there's only two x-intercepts, there's only one x value we need to plug in. So pick something between -3 and 2, plug it in, and then see if you can come up with a sketch of the rest of the graph. Alright, so for things we could plug in here, really anything between -3 and 2 would be fine, but I'm going to go real easy here and plug in 0. Now, you could probably do this by hand, but I'm going to be super lazy and go on Desmos to do this just to make sure I get the right value. And if you have this available, you should probably also go about it this way, especially if you're plugging in multiple points. But let me write out my function. So f of x equals 1 divided by 6, and then we've got x plus 3, x minus 2, and we'll square that. And I just want to plug in f of 0. So that'll give me 2 for an answer. There you go. So let's see if we have enough information to graph this now. I don't have super huge values, so I can probably just use grid lines that are going from like -6 to 6 and in both directions, something like that. So we have the x value -3, that was a 0 right here. F of 0 was 2, so we have 0, 2 right here. And we also have the x-intercept of 2, so that's 2, 0 right here. And it looks like our end behavior is starting low, ending high. So we would be starting below the x-axis here, going through this x-intercept, going through this point we got to come back down at some point and go here, and then going up, because we have to go up in order to end above the x-axis. So that would force us to bounce off of that x-intercept. Now you can also use what you know about root behavior to determine if you made the right decisions. We had a single root at -3, so we should cross through the x-axis, and indeed we do. This double root at 2 is telling us we should bounce there, so you can still use that information. It's just you don't need to use it because now you have these points above or below the x-axis that kind of force you to go the right way in order to go through them. Now, what if you didn't have these two x-intercepts? What if you only had one x-intercept, but you still needed to come up with something approaching an accurate graph? So if you only have one x-intercept, it's a good idea to plug in multiple x values near 0, maybe everything from -2 to 2, just to get a better picture of what's going on. Before we dive into our next example, we're going to go over a few interesting properties of polynomials and little tricks we can use here and there. One of these is something called the location principle, which is for locating zeros of a polynomial. This says that if p of a and p of b have different signs, then p of x has to have at least one root on the interval from a to b. So just kind of putting this into English, if I plug in two x values to a polynomial and I get different signs, that proves that I had to cross the x-axis somewhere between those two x values. Just to give you an example, let's say p of 1 was -3 and p of 2 is 1. There's some polynomial that I just plugged these into and got these back. Or maybe they gave me a table with these values. That would tell us that p of x had at least one zero between the x values 1 and 2. So in principle, this is useful if they give you a table and you have to prove rigorously that there's a zero, at least one zero somewhere for this function. You could use this type of reasoning to prove that. You could also use this to help you kind of zero in, no pun intended, on the roots of an equation. If you've got a list of possible rational roots and you've already kind of figured this out, maybe you would start by testing the rational roots that were between 1 and 2 before you looked at some of the others. In any case, there's some other things we want to talk about here, and one of those is turnaround points. So polynomials, you might have noticed they have some turning points in them sometimes. They have two types of turning points that are possible. One of these is called a local maximum, which is the highest point in an area, basically a hill. And we'll see some examples of that later on. But the reason we're calling this the local maximum is that it may not be the highest point for the entire graph. Especially if this graph goes to infinity in both directions, it won't have a highest or lowest point. But it could have a highest point just in a certain area. We can also have local minimums. These are the lowest point in an area, or the valleys. Now, there's a little neat trick you can use to figure out how many turning points a polynomial could have. It turns out that a polynomial of degree n is going to have at most n-1 turning points. So, for example, something to the 4th power would have at most 3 turning points. It could have less, but it won't have more than 3. That's what this tells us. And this is useful kind of like the fundamental theorem of algebra, which says that you have at most as many rational roots as you have for the degree. That's kind of a very specific version of it, but it tells you kind of when you can stop looking for these things. So at this point, we are going to do an example using a little bit of technology, a little Desmos. We're going to have you identify the x-intercepts and points where we have maxes and mins, local ones, for this f of x function, and then determine intervals where the function is increasing, which means going up, or decreasing, going down as you move to the right. So you could find all these turning points with calculus without using a calculator, but in practice, if you don't have calculus available to you, graphing calculator is the only way you can reliably find these. So pause the video and let's start by seeing if you can find the x-intercept, just to make sure we're on the same page here. All right, let's see how that went. So let's go to Desmos. And on the graphing version of Desmos, let me enter f of x in there. So we've got x cubed minus 3x squared plus 6. And let's just move this up here. So I see here that we've got one x-intercept that I can see. Let me just zoom out and make sure there's no other ones that are hiding. And it's pretty unlikely that there are any. So I think we're pretty good with this one. We also have 2 turnaround points. Now we know that since this is 3rd power, there's going to be one less than that for the total possible number of turnaround points. So there could only be at most 2, and here they are. So that at least tells us there's no more bends or twists further off the window that we're not seeing. So if you want to click on these gray spots here, these are the x-intercepts, and also they always give you a gray spot for maxes and mins that you can click on just to kind of hold those in place. So here is our graph, just cut and pasted it. And hopefully you were able to find the x-intercept here, which was negative about 1.20. If we round to 2 decimal places, you could go more if you wanted to. So if you're on the same page still, then pause the video and see if you can go on and find the maxes, mins, and increasing, decreasing intervals. All right, so let's do the rest of those. So just going kind of from left to right here, we see that we've got a local max, a highest point, a hill, at 0, 6, and a local min here at 2, 2. It's a valley. Now for increasing versus decreasing, let me actually do increasing first. Our graph is increasing, moving up as we go to the right from negative infinity to this spot right here where we hit that max at x equals 0. So I'm going to say for x less than 0, we're increasing, and also for x greater than 2, from 2 on to infinity. For decreasing, we are going down between 0 and 2. So we're going to say 0 less than x less than 2 for that interval. And that'll be it for this one. So speaking of turning points, if you're taking this in the CP non-honors course, then this is a point to turn off the lesson, temporarily at least, and try out some homework problems. This is the end of part 1 for you. If you're doing the honors, then let's just keep on going. Welcome back. Whether you're rejoining us from the CP or continuing on from the honors, at this point we're going to introduce the concept of even and odd functions. So what is this all about? So an even function we are defining as a function that has y-axis symmetry. More specifically, we're defining this as a function for which f of negative x equals f of x. Now, what does all this mean? Let me give you an example of an even function. So I'll show you something on Desmos here. Sort of the poster child for an even function is f of x equals x squared, our good old-fashioned parabola. We can clearly see that this has y-axis symmetry. I can reflect this over the y-axis, and I'm going to get the exact same shape that I started with. Now, what is this whole f of negative x equals f of x business? Well, that's just saying if I plug in a positive or negative version of the same number, I'm going to get the same y value back. So for example, if I do f of 1, that gives me 1 back. And if I do f of negative 1, that still gives me positive 1 back. And it doesn't matter what number this is. If they're negative and positive version of the same thing, I get the same thing because I have this y-axis symmetry. Now this is in contrast to an odd function, which is something that has origin or rotational symmetry, which I'll show you in a minute. So the rule for this one way of proving something's an odd function is if f of negative x equals negative f of x. Let's see what this one actually looks like on Desmos. So an odd function, an example of that would be x to the third power. So we see here that if we were to rotate this polynomial about the origin, rotate it 180 degrees, then this part up here would now be this part down here, and we'd actually have the exact same thing that we started with. In terms of that f of negative x, negative f of x business, this is just saying if I plug in a negative x value from what I did before, I'm going to get the negative version of the y value back. So if I've got 1, 1 on here, I've also got negative 1, negative 1. Now that we've got that background on even versus odd, we're going to use that to figure out if this g of x function is even, odd, or neither. And let me be more specific. We're going to figure this out without actually graphing it out, because if I could just graph it out and eyeball it, I could probably tell pretty well what kind of symmetry it had. Now, you might be wondering, why do we care if something's even, odd, or neither? In practice, if I'm being honest, this comes up in the weirdest places, usually on some standardized test like the SATs or an AP exam, where they give you not a whole lot of information, but if you understand this, then you'll be able to know just enough about the function to answer the question, knowing how it's shaped and things like that. So anyway, how do we figure this out without a calculator? So there's an even and an odd test based on this f of x sort of business up here. The even test, you just have to find f of negative x and compare it with f of x, because if those two things are equal, then that proves that this is an even function. Now, when I say f of negative x and f of x, I mean you literally have to plug negative x in to the function and see if you get the same thing you started with. So pause the video and see if you can determine whether g of x is even. Okay, so we have g of negative x. That's going to be 4 times negative x to the 5th plus 6 times negative x. And if we simplify this, if you raise a negative to an odd power, it stays negative. So we have a negative 4x to the 5th, and then this is going to be negative 6x. Now, comparing g of negative x and g of x, these two things are not identical, they are not equal. That proves that this is not an even function. It does not have y-axis symmetry. Now there's also an odd test that we can use, and the odd test, based off of this sort of reasoning up here, basically says find negative f of x and compare it with f of negative x. And if those are the same, you've got an odd function. So pause the video and see if you can run that test on this function and determine whether this is odd. Alright, so we've already figured out g of negative x, so we don't have to do that again. We do need to still figure out negative g of x, however. So negative g of x is just going to negate the whole g function. So this is going to be negative 4x to the 5th, and then distributing here we have also a minus 6x. So here's g of negative x, here's negative g of x. If you compare these two, they are exactly the same. This proves that g of x is an odd function. Now, we kind of lucked out that this worked. What if we had done both of these tests and neither of these had actually come out the same? Well, if f of x fails both tests, then that means the function is neither even nor odd. It's entirely possible we have a function that doesn't have any of those types of symmetry, origin or y-axis symmetry. Now, you might also be wondering, what's to stop a function from being both even and odd? I mean, it's kind of a funny question because we think numbers can't be both even and odd, but it turns out there is one little exception to all of this stuff with functions. So normally, I mean, if you test this and it comes out even, you wouldn't have to test it to see if it came out odd. There is one function though, and that is, let me show it to you on Desmos. If I give you the function f of x equals 0, basically the x-axis as a function. This has y-axis symmetry. It also, if you were to rotate this line, you just get the same line. It has origin symmetry. So f of x equals 0, that's the one counterexample where you have a function that's both even and odd. But that's kind of the exception. Typically, once you've figured out that it's even or odd, you don't have to test for the other one. So now that we've run through those various tests, pause the video and see if you can figure out whether this f of x function is even, odd, or neither. Alright, so to figure out if it's even, which I usually run that test first, we'll have f of negative x, which is just negative x squared minus 8. Negative x, if I square that, becomes positive x squared, and then we have a minus out in front still, so that's negative x squared in total. We still have that minus 8, which is completely unaffected by whatever we plug in for x. Comparing this with the original f of x function, we see that these are the same function. So this proves that this is an even function. And again, because this is not that weird case of f of x equals 0, we don't have to test to see if it's also odd. We can just stop here with, hey, it's even. Now that we've run through a couple of those even-odd tests, you might be wondering, why are the functions called even and odd when it's all about types of symmetry that we have? What's this whole even versus odd thing? So let's take a quick look back at the two that we did. So we had This one right here, where we had 4x to the fifth plus 6x, and that turned out to be an odd function. It turned out to have origin symmetry. And then we had the one right after it, negative x squared minus 8, which turned out to have y-axis even symmetry. Well, look at the exponents here. Notice that the evenness of this exponent is causing this negative x that we plugged in initially to not really make much difference for when it's fully simplified. And if we take a look at the odd one here, the fact that these two exponents were odd meant that when you plugged a negative x into those, it negated everything you plugged that into. So it was guaranteed to pass the odd test at that point. So it really is all about these exponents, actually. It turns out, as we saw there, that if your polynomial has all even exponents, it will pass the even test. And by the way, constants count as even exponents. In contrast, if your polynomial has all odd exponents, it's going to pass the odd test. And if there's a mixture of those, both even and odd exponents, it's going to fail both tests, because some of the things are going to remain the same and some are going to be negated, and it won't do either of those things consistently. So we can actually use this to make short work of some problems, at least if we're not required to show any work. With that in mind, here is an example. We want to determine this last one, whether this is even, odd, or neither. Pause the video and use whatever methodology you would like, other than graphing, to figure that out. Alright, so looking at our exponents, we see that we have both even and odd exponents. That means, by our reasoning up here, that f of x is neither even nor odd. Now you might be wondering, why didn't I just kind of tell you this in the beginning, and why did we do all those somewhat long convoluted tests? Well, this shortcut does work for polynomials. It'll work every single time. However, you're still going to need the full even and odd tests for other function families, such as trigonometric functions and absolute value, and all of those that don't have this little exponent hack that you can use to shortcut the process. Also on your homework, I'm going to make you do the full even-odd test just to get practice. Speaking of homework, that's the end of this lesson here. So if you were watching this video as part of a course and not just for fun, give those problems a shot, both the evens and odds. Until next time, Mr. Sutton signing off.